All right, so hopefully you tried the examples from last time. We're going to go through those. But before we do, I want to show you that trick I promised to show you. So partial fractions, of course, continue. So I'm going to show you a trick to find coefficients for non-repeating linear factors. So the trick I'm about to show you doesn't work in any other case. It works for non-repeating, meaning the factor doesn't have a power like a square or a cube on it, and it has to be linear, meaning it looks like ax plus b or whatever, for non-repeating linear factors. Now, in the main example that I showed you, that I spoke about, that was the 1 over x squared minus 5x plus 6, which you know you could actually factor into x minus 3, x minus 2. So this has non-repeating linear factors. Okay? So now you're going to rewrite this as x minus 3 plus b over x minus 2. Now here's something that you can actually do. Let's say we multiplied by one of the factors. Let's say, so I don't multiply by the entire denominator. I'm going to multiply by one of them, say x minus 3. What's going to happen is I have 1 over x minus 2, and I would have just a plus b times x minus 3 over x minus 2. Now what happens when you plug in the convenient value, say x equals 3, what's going to happen? You have a just solved for already, right? Now I want you to notice what this is going to happen here. Well, maybe you'll see the pattern on the next one. Now suppose I multiplied by the other term. Multiplied by, say, x minus 2. Multiply, whatever. What would have happened? Well, you'd have 1 over x minus 3. You would have a times x minus 2 over x minus 3. And you don't have b here. Now if I plug in x equals 2, notice what happens. You have b kind of by itself. And you would automatically get minus 1 equals b right away. Now, what can we learn from what I just did? I want you to notice that here's a, right? The denominator is x minus 3. If I go over here and I actually plug in the x value that makes that denominator 0, except I don't evaluate it at the x minus 3, that's actually the answer for A. Correspondingly for B, if I look at the x value that makes his denominator 0, go to the original, cover up that factor, and plug in that number, I would automatically get the answer for B. Right? This is called the cover-up method. And it's a special case, let's say, of a larger theorem. It's called the residue theorem. Now, you're not going to hear about that guy until you're in a complex analysis class, which at City College, if you're an engineer, you could take the class Math 395. Other than that, there's only a graduate course. I think it's A6300. So complex analysis, that's like magical calculus right there. There are lots of things that complex analysis is useful for, both from the applied side, but also from the math side. A lot of things that we can actually do in regular calculus, if we just imagine that x is a complex number, suddenly we can find answers, and quite easily, right? So there's this major theorem there that talks about, one of its applications is to actually solve for things in partial fractions. The other cases are more complicated than the one I just told you, so I'm not going to actually tell you that. It's going to involve multiple derivatives to figure out the coefficients. But for linear factors, it's actually pretty easy, and it's called the cover-up method. Pretty much cover up the coefficient, the numerator that you want to find, cover up his denominator in the original, and plug in what would make that denominator 0. So, to give you another quick example. 5 over x minus 5 times x plus 1. Right? What are the partial fractions for that? Well, it's going to be something over x minus 5, something over x plus 1. What are the tops? Well, x equals 5 is going to make that 0. Cover that up, plugging x equals 5. 5 over 6 is going to be the answer. X equals minus 1 is going to make that 0. Cover that up, plug in x equals minus 1. Minus 5, 6. And you can go through one of the methods that I taught you last time, and you'll get those as the answers. But now it's like, you can kind of do it in your head, right? So if anyone else just knows the other two methods that I told you, you can do this and like, what are you, a math ninja? What's going on here? Like, you can just do it just by looking at it. 1 over x minus 7 times x plus 1. You know that's going to break up into x minus 7, x plus 1. 7 is going to make that 0. Cover that up, plug in 7, 1/8. Minus 1 is going to make that 0. Cover up that, plug in minus 1, minus 1/8. Check it, that's going to be the answer. This is called the cover-up method, right? Because you just cover up the guy whose numerator you want to find, plug in what would have made that 0, and that's actually going to be the answer. Yeah.
Can you explain that again? I'm kind of confused. So what did you plug in for the x in order to get that 5 over 6?
Whatever makes the denominator 0.
0? Okay.
So I look at this denominator, 8 minus x minus 7. What makes this 0?
7.
7 makes it 0. So I go here, I cover up the x minus 7, and I plug in 7.
Oh.
Right? And that's going to be the answer. And then x equals minus 1 would make this denominator 0. Cover that up, plug in minus 1, and you'll get the coefficient. That works for non-repeating linear factors. It's actually a nice little shortcut. It's called the cover-up method. There's a more general theory that could deal with repeating factors as well as non-linear factors, but it's a much bigger theorem to state, and I'd have to explain a lot about complex analysis for it to even make sense to you. So, but in the meantime, you see one of these guys, you can actually do that trick. And you can do it in pieces. So for example, if there is 1 over x minus 2 times here x squared plus 1, you know that this is going to break up into something over x minus 2 plus some bx plus c over x squared minus plus 1. Now the trick I just told you is not going to work for that guy because it's not a linear factor. However, it's going to work for this guy. I can cover this up, plug in x equals 2, and 1/5 is going to be that. So now you only have to do work to find the b and the c. Right? The guy that's the non-repeating linear factor, you can always find it via the cover-up method. Cover up the denominator of that guy, plug in the x that would make that 0, and that's actually going to be the coefficient, the numerator. So that's just a nice quick trick there. Yes?
What if there's like 3 in the denominator instead of just 2?
Like this?
No, like what if it's like x minus 2, x plus 1, like 3 different ways to factor that?
Like you have x minus 2, x minus 2, x plus 3, and say x squared plus 1, like that?
Or even just like x plus 1. Like what if they just be
Like this?
Yeah.
Yeah, you can still do it.
Okay.
So, two makes this 0. plug in 2. That's going to be 1 over 5 times 3. So that's 1/15 is going to be that coefficient. Minus 3 is going to make this 0. Cover that up. Plug in minus 3. That's going to be 1 over minus 5 times minus 2. And x equals minus 1 is going to make this 0. Cover that up. Plug in minus 1. That's going to be 1 over minus 3 times 2. So the coefficients are going to be 1/15 over x minus 2 plus 1/10 over x plus 3 minus 1/6 over x plus 1. Those will be the partial fractions. You can do it as often as you'd like, as long as you have non-repeating linear factors. So, can save a lot of time. Yes, of course, and I mean, I don't know if this is good for you. It depends on how you approach it. But yes, I'm here, I want you to learn, but I also secretly have the ambition to train my own group of math ninjas. So when I give you guys advice and when I'm teaching you, I'm not just teaching you just to learn this thing, I'm teaching you to be the best at this thing. Like you can go out there and they could stand you up against any other Cal 2 student in any other class and you're like just gonna decimate them. Like, oh, you want to challenge me to integrals? Right? And sometimes when I'm writing quizzes, I even factor this in. Like, okay, so I expect them to see a trick right here. So while any other Cal student is going to take 3 minutes to do that, my student should take 10 seconds to do it. And that's how I'm writing the quizzes. Just so you know. I expect a lot from you. But it's not unreasonable. It is doable. That being said, let's get to the examples. Let's see how you guys did on the ones that we wrote down last time. How much space am I going to need? Let's start over here. So that's the curve method. Saves you a lot of time in certain situations. But of course, method 1 and method 2, like I said, it will work in all situations. But this one, in these special situations, you have that. So we had 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x. All right, someone tell me how to do that one. All right, so first thing, what did you have to check? Is it proper, right? Highest power on top is a 2, highest power on the bottom is a 3, so it is proper. So now I can just go into the method. The next step would be to factor the denominator, which is x times x squared plus 2x plus 1, which is x plus 1. So, how would this actually break up into partial fractions?
A over x plus b over x plus 1, c over x plus 1.
Now, based on what I told you, you should be able to find A readily.
Professor,
How would you find A? Yes?
C has to go with x, cf.
No.
No? Why?
Because the factor is x plus 1.
Oh, yeah.
It's a first degree, so we need a 0 degree on top. How do I find what goes on top of the x?
It has to be specific.
Right, so I cover that up and plug in x equals 0, what would you get? 6. So that's automatically a 6. Now I only have to focus on the b and the c. How do I find the b and the c?
Can't you do the thing the same way?
Yes.
No, because it's a repeating factor, so it doesn't work.
Oh, yeah.
How do I find the other ones? What was the next step?
You could multiply both sides of the factors.
So I'm going to multiply both sides by the denominator on the left. I'm going to have 6 times x plus 1 squared plus b times x plus 1 plus c times x. Okay, now what? Huh?
like X equal.
Do you see any convenient x's?
Yeah.
What?
X is equal.
Minus 1 is convenient. I can just get that out of the way and solve for the c.
0.
This is going to be 5 minus 20 plus 6. That's just going to be minus c. So what is that? Huh?
He's 9.
C is going to be 9.
Yeah.
So c is going to be 9. Then what are we going to do for the other guy?
do 0.
X equals 0 is not going to help. That's going to kill b and c. I want something that's going to let b live.
What about
Just 1.
1 could make b live, so if I plug in x equals 1, I would get 5 plus 20 plus 6 is equal to, 6 times 4 plus 2b plus c, which is 9. So now b is the only unknown here. And if we solve that for b, what do you get? Get minus 1?
Yeah.
Okay, so that's the partial fractions. So this guy, p equals 6 over x minus 1 over x plus 1 plus 9 over x plus 1 squared. That would be that. What do we do?
Factor out the denominator with x.
First you check if it's proper.
Oh, no.
That's always the first thing. Is it proper?
Yes.
Yes. The highest, it's a 4th degree on the bottom and a 3rd degree on top. Now that you know it's proper, the next step is to factor the denominator. This is going to be x times x minus 1 times x squared plus 4. And this is 2x cubed minus 4x minus 8. And this is going to look like a over x plus b over x minus 1 plus c plus b over x squared plus 4. A we can actually find. How? Cover this up, plug in x equals 0, what would I get?
Minus 2.
I would get minus 8 divided by minus 1 times 4. For the b, I can cover that up and plug in x equals positive 1. That's going to be 2 minus 4 minus 8 over 5.
I have a question, Professor.
Yes?
When we get to the same thing, like x plus 1.
It's not a non-repeating factor.
Yeah.
The trick only works for linear non-repeating factors. Okay, so other than that, we multiply both sides by the denominator on the left. So we have 2x cubed minus 4x minus 8 equals, what is this going to be? That's just going to be 2.
Yes.
And if I multiply that, the x's are going to cancel. I'm going to have an x minus 1 times x squared is 4. Then this one is going to be what?
Minus 2.
Minus 2. And the x minus 1s are going to cancel, so that's x times x squared plus 4. Then I'm going to have plus cx plus d times x times x minus 1. How do I find the other guys? to try to plug in a -1.
I guess what we.
So this would be -2 plus 4 minus 8. -1, that'll be 2 times -2 times 5. -1, that's 2 times -1 times 5. -1, that's going to be minus C plus D times -1 times -2. So this is going to be -10 plus 4, that's -6. This is going to be -20 plus 10. This is going to be a positive 2, so that's -2C plus 2B. I could divide everyone by 2, I suppose. So this is -3 equals -5. Because that's going to be -10 divided by 2, so it's -5 minus C plus D. So in other words, I would get that minus C plus D is going to be equal to positive 2, right? Now, can plug in another convenient number. What do you want to try?
2.
2. So 0 is already taken, 1 can't work, that's already taken. -1, so I guess 2 is the next option. If my x equals 2, I would get 8 here times 2, that's 16. 8 minus 8, well that's actually 0. And if I plug in 2 over there, I would have 2 times 1 times 8 minus 2 times 2 times 8 plus 2C plus D times 2. So what does that mean? 0 is equal to 16 minus 8 times 4 is what? 32 plus 4C plus 2D. So this here is a -16. I can divide through by 2. So this is 0 equals -8 plus 2C plus D. Or in other words, I get 2C plus D equals 8. And I can throw this guy in here. Minus C plus D equals 2. How do I solve for C and D here? I can say subtract. This is equation 1, that's equation 2. Take 2 minus 1. That would be 3C equals 10. 3C equals 6. So my C equals 2. And if my C equals 2, that means that D is 4. So, what is P? My P is equal to
The right
2 over x
-2.
minus 2 over x minus 1. My C is 2 plus 2x. My D is 4 plus 4 over x squared plus 4. You guys got the same thing? So that's all. C 8 x cubed plus 13x over x squared plus 2 squared. All right, what happens here?
check it's proper.
Check if it's proper. It is?
Yes.
So what happens?
That is equal to A.
It's already even fully factored, right? So this is equal to
A over x squared plus 2.
AX plus B.
Oh, sorry.
ax plus b over x squared plus 2
Plus cx plus d of x squared plus 2 squared.
multiply both sides by the denominator on the left, I would have 8x cubed plus 13x equals ax plus b times x squared plus 2 plus cx plus d. And just for some variety, let's do method 2 here, just in case someone likes that and they did all the problems with method 2, they can have something to compare to. So I want to apply method 2 here. What do I want to do?
You want to expand the right side?
I'm going to have to multiply out over here. What would I get on this side if anyone did that way?
X cubed plus
2x plus 3x squared plus 2b plus cx plus d.
Then what do?
group the terms.
Group like terms. So x cubes, they're just ax cubes.
Plus bx squared.
X squares,
Just bx.
there's just bx squares.
And then cx and 2ax, 2a plus c.
So we have 2a plus c, all of that is grouping the x's.
And d.
And then we have 2b plus d is the constants. So what does that allow us to set up here? As soon as I get erased, we can go.
A is equal to 8.
Right, so we have right away a is equal to 8,
B is equal to 0.
b is equal to 0.
2ac is equal to 13.
2a plus c equals 13.
And 2b plus d equal to 0.
2b plus c equals 0. But I already know what a is and b is.
That's d. isn't it?
That's d?
Yeah.
So from this, my a is 8, so that's 16, move it over here. C is going to be 13 minus 16. And my b is 0, so that means my b is 0. It's gonna be a
To eat x.
8x over x squared plus 2.
Minus 3x.
D is also 0, yeah, so it's minus 3x over x squared plus 2 squared. And those are the partial fractions. You guys are all getting them? Okay, good. Now once you get them, the next thing is to really try to increase your speed. Because on one hand, not only do I expect you guys to be math ninjas, but I'm not writing your final. There's a certain amount of time that you'll be allotted. And yeah, you need to be able to do a lot in that time. The final's going to feel really cramped and really intense, so you need to get used to that feeling. Okay, what do we want to do here?
Make it a proper fraction.
Check it's proper, is it?
It's not.
No, what do we do?
Make it proper.
You can bring all numerator to denominator.
By doing what?
Add 1 and negative 1. Or negative 1 and then fraction.
Minus 1 plus 1. So this really breaks down into 1 plus 1 over x squared minus 1. How do I continue?
You partial fraction the x squared minus 1.
What needs to happen?
Factor out x squared.
What are the partial fractions?
One half and minus 1.
Minus 1.
See? You guys are just doing it in your heads now. Meanwhile, the kids from the other class are like, damn it, find these A's and B's. So that's the cover-up method. Okay, now we know how to do partial fractions. Let's apply it to some integration. So, A This is one of the examples that we did by trig substitution before. And I mentioned that when you have an odd part in the denominator, you have an option of avoiding trig substitution. I just taught you what you need to know to avoid that option, so that should be an interesting one. You can compare your solution to this, to the solution that we had with trig substitution, and see which one you like more. We're going to do those guys. More specifically, you are going to do those, I'll be the scribe. Okay, go, tell me what to write down. Pardon.
It's not proper.
It's not proper. What do we do?
So you have to do this trickery.
Okay.
-1 plus 1, I think. I don't really understand.
Minus x for,
Well, one, you can just write the denominator in the top. Just write it down. Right? Figure it out later, right? So you go that, you write it down. Now you just kind of see, what do I need to add or subtract to kind of get back to the original?
Oh,
Right? So here I have a minus 4x. The original is minus. Add an x.
And add
5. Right? So this breaks up into what?
1 plus x plus 5 over that.
So now that's broken into two parts. And what can we do here? So now, of course, the 1 dx, the integral of 1 dx, that's not something we're worried about. So we're mostly worried about this guy right here. How do you deal with him?
Can you divide 4 for each?
Can you do what?
Can you divide 4
Divide 4 where?
from the x square and then 4x and 3 over 4, so you can get
To what end? Why would you want to do that? Yeah,
you could factor it.
into what?
2x minus 3 and 2x plus 1.
Yeah, that'll give you the 4x squared, that'll give you the minus 3, middle term, minus 6x, outer term, plus 2x. That gives you that, so that's factoring. You either have to do the AC method, which is not very efficient, but it'll get the job done. Or you can just do that trial and error, the kind of thing that I just told you. The multiplication of the two close ones and the two far ones must sum to give you the middle term. So that's that. Knowing that, what's the next step?
partial fraction.
What are the partial fractions? The coefficients, the tops. Can do cover method. These are non-repeating linear factors. So what goes on top of the 2x minus 3? Well, you cover up the 2x minus 3, and you plug in x equals what? 3 over 2. So you'd have 3 over 2 plus 5 over 3 plus 1. That's going to go on top of there. What about the 2x plus 1. X equals minus a half is going to make that 0, so I'm going to cover that up and I'm going to plug in minus a half, so I'm going to have minus a half plus 5 over
Minus 4.
minus 4. Right, so if I have 3 over 2 plus 5 over 4, I can multiply that by 2 over 2. That's going to look like 3 plus 10 over 8, so that's 13 over 8. And if I have the minus a half plus 5 all over minus 4, I can multiply that by 2 over 2. That's going to be like minus 1 plus 10 all over minus 8. So that's going to be minus 9 over 8. So those are the partial fractions. What are the integrals? Integral of 1?
X. And then 2x minus 3.
What's the coefficient?
13 over
13 over 16. This one is going to be ln of 2x plus 1 plus c. Coefficient?
9 over 16.
Negative 9 over 16. That's the answer. Questions? Yes?
When you're finding the antiderivative, right, aren't you supposed to add 1 to the
Add 1 to what?
to the numerator, so it wouldn't be 13 over 8 plus 8 over 8? Or,
I'm not. You mean to get from here to here?
yeah, like wouldn't you add 1? So like, wouldn't that be 13 over 8 plus 8 over 8?
Why would you add 1?
Like that, right?
What rule are we applying here?
You're supposed to-
We want the integral of 1 over x.
The integral of 1 over x is ln of absolute value of x. That's the rule we're applying. There's no plus 1 anywhere. So if I have 13 over 8 over 2x minus 3, I think of that as 13 over 8 times the integral of 1 over 2x minus 3 dx. I would do a u sub, u equals 2x minus 3, my du is going to be 2 dx, which means 1/2 du equals my dx. So that 1/2 multiplies by this, that's going to give you 13 over 16 integral of 1 over u du. That gives you the ln of absolute value of u. Your u is the 2x minus 3 and the 13 over 16. So there's no add 1 because the formula doesn't say so. Everything we do, there's a formula in mind for why we're doing it. But of course, when you're doing a substitution, your du is going to be a constant. You kind of just do that in your head. You know, you divide out the constant. Only when your du is a constant. It doesn't work in general. Okay, see this integral. What do you try?
Factor the denominator, so difference is squared.
Now, radical is going to be an issue, though. How do you take care of it? How do we make that something that we can deal with? Okay, what would you,
Just set, u square root of x, square root of x into dx.
then that's gonna become what? So your u is equal to square root of x, so this square root of x on top is a u. On the bottom, that's u minus 2 times u plus 2. And then the dx becomes 2u du. So substitution. So what happens here? So this is a 2u squared over u minus 2 times u plus 2. Where do we go from there? You guys already slightly messed up, but we can dig ourselves out of this hole, actually. Yeah.
I was thinking, what if you just change that back to like x minus 4, like from the beginning?
Yeah. So we're gonna have to undo some that we did.
Yeah.
Lost time, inefficient. Jhevon is like, 5 minutes left, now you have to correct some mistake. What would have been the correct approach?
Multiply.
Let's start from the beginning. You see that, what do you do? What do you think?
Is it partial fraction?
Oh, the first
No.
thing you think is, will a substitution work?
No, that's the third
That's
thing
the
you
third
think.
thing. Is it a rule?
Is it a rule? No. Can I simplify that to be a rule? No. Substitution. The first thing you should have done was that. It's ugly. Well, how am I going to deal with a radical x and an x? Substitution. It's always going to be the third thing you think. You're going to do that. Then you're going to have the 2u du is equal to the dx. You're going to plug this in, and it's going to look like this. And now it's more obvious for what to do, right? Remember your training, grasshoppers. There's a reason I tell you to think of things in a certain order. Because otherwise you're just going to feel a lot like, what the heck? What am I supposed to do now? You always do the same thing. Go back to the programming. Step 1, is it a basic rule? Step 2, can I simplify it? Step 3, is a substitution going to make things nicer? That's the obvious substitution. That's nicer. We know how to deal with that now. How do we deal with it?
Got everything by u squared?
No.
Bring the numerator to the top.
Bring the denominator to the top. It's not proper. Subtract 4, add 4. This goes to 1 plus 4 over u squared minus 4. How do we continue?
Now you can just back up twice.
What goes on top of that?
Is it negative 1 over 4 or positive 1 over 4?
Where?
On top of the coefficient. Because they're not repeating the numbers. So you
Yeah. This is a 4, by the
can. Oh.
way. Yeah, so
It's not 1? So it's 1.
that one. Integral of 1?
Oh, you.
U. Integral of that? Integral of that? And it's 2 times all of that. So this is going to be 2 times u was the square root of x plus ln of the square root, just right, it says ln of the square root of x minus 2 divided by the square root of x plus 2. That's our guy. you're training grasshoppers. Looks ugly, what do I do? Substitution. It's not a basic rule, no way to really simplify that. Substitution. If a substitution doesn't kill the problem for you, at the very least it'll put it into a form where it's more you can see what to do a lot easier. Like seeing what to do here and seeing what to do there, a different ballgame. Like this is, yeah, it can just, having that radical x there is kind of confusing. Didn't do the substitution first. Of course, you realize you got here where you had to undo something that you did to kind of fix it. Like once you take the steps out of order, it can kind of get messed up. It's plus one. Okay, what do we do with that one? What do you want to substitute?
Professor, just on Smith is already past 5. I'd have to go to that important moment with Dash.
Yes, I remember you telling me, and I told you you could leave quietly when the time came.
Just to let you know.
So we have u squared plus 1, u minus 1. Now what? Huh? Yes.
Split it up into two fractions.
So how did it?
Like ax plus b over x squared plus 1.
Well, u plus b.
That's c.
Okay, so how are we going to find those guys?
You can do the cover up method for c.
So I can find c, cover this up, plug in u equals 1, give me a half here. Other than that, I am going to realize that 1 equals au plus b times u minus 1 plus a half times u squared plus 1. So now I have to solve this for a and b. What am I going to get?
Use 0 for u to find b.
Plug in u equals 0. We would have 1 equals minus b plus a half. So this means that b is equal to a half, right? Move that over. Wait, what did we plug in? We plugged in u equals
0.
0. So the a is gone, that's minus b, and that is plus a half, right?
Yeah.
So move that over, you get positive at minus a half. Okay, now what?
U equals 1 plus A.
Use u
U equals 1 is going to kill the a.
You can use u equals 2.
U equals 2. This is going to be 1 equals 2a minus a half times 1 plus, plug it in 2 here gives me 5 over 2. So I would have 1 equals 2a plus 2, right? And so bring the 2 over, you get minus 1 divided by 2. You also get a equals minus a half, right? So this whole integral would now become, factor out a minus a half, and I would have u plus 1 over u squared plus 1 minus 1 over u minus 1. How do I deal with that integral? Sarah, you see something?
It would be negative, okay, it would be negative 1/2, okay? ln, absolute, but there's gonna be a number in front, I think it's u ln absolute value of u squared plus 1.
No.
No. Oh wait, what is u equal? You said u, not quite sure.
So you can split the integral into two and just take, right, like, the integral of u plus 1 over u squared plus 1.
Yeah.
Minus the integral of 1 over u minus 1.
That's what I would do next. Why would that be what I do next, by the way?
It just looks nice.
There's no, just launching a prayer, like you had no idea?
Now you can
So you can do the ln of whatever down and then
Yeah.
for each
There's
term.
also another thing.
You do trig substitution in the first one?
No, I don't want to do that. I don't want to do that.
No, come on, no.
Isn't useful.
But what else would make me do that? What would make you think of doing that? Like splitting these up was the, feel good about that.
Well, now you can product rule, right? I mean, at least for the second two fractions, you can, u to the negative 2, you can product rule that. And then,
I'm not sure, product rule? Product rule is
I mean, not product, power rule, that's what I meant.
This one?
The second one.
This?
Yeah, u to
No.
the negative 2. No? 1 over, all kinds of ideas in my head.
So I mean, yeah, I need you to find the right ones.
Could you do
That's the whole point of me
could you
asking
do,
this
like-
question.
Could you do like a second u substitution? Like a u prime substitution?
No, here's the question. You got up to this point. Why was this the correct step? Why did I do that as opposed to doing anything else in the world? Huh?
You're thinking you have to simplify it? Like that's the first thing you think, you have to simplify it?
Sure, I gotta simplify it. Why is this the simplification I chose?
Is it simpler?
I mean, it's like a fraction property, right? Where you can split it up like that.
So nothing here strikes you as being familiar.
It's a basic.
Isn't the middle one the tangent?
The middle one is an arctangent.
Oh.
You see, Jhevon forced you to memorize a bunch of formulas, right? One of these formulas happens to be, if you see something like this, it's that, right? I saw that here. It wasn't random. I didn't just, oh, let's try to make it simpler. No. I have a bunch of rules in my head, and I'm looking for one of these guys to show up. I'm like a hunter. I'm like waiting for the, I want one of you guys to show your face, because then I'm going to kill you, right? I do substitution, I do all this stuff, but once I'm here, okay, I went through a process to get this integral to a point where it's relatively simple. Now, how do I finish it off? The formulas are going to help me finish it off. Now is what quiz 1 in Jhevon's quiz is all about. When you get to this step, that's what you want. All those guys you've memorized for question 1 of the quiz. they're the guys they're going to use now, right? You went through a process to bring you to a point where the rules that I had you memorize is going to take you home, right? I did this because I remembered this. Not because I'm just trying something, or I feel like it might be simple. No, there's a specific reason. This was the reason. Okay? All right, so that's why I went from this step to that step. There's a rule in my head that says that's a good idea. Because now that guy's easy, and I was gonna, later I'll worry about that guy, but I'm just picking them off one by one, dividing and conquering, splitting everything off that will give me a nice formula. And the other guy, I'm just gonna, now that is, how would I do that? That's a substitution, right? T equals u squared plus 1, my dt is gonna be 2u du. So that ultimately is going to be 1/2 ln of u squared plus 1. This guy is going to give me my arctangent. This guy is going to give me an ln. It's minus 1/2 times all of that. Now I'm going to do my back substitution. What was my u originally? My u is e to the x. So this is minus 1/2 times 1/2 ln of e to the 2x plus 1 plus tan inverse of e to the x minus ln of e to the x minus 1 plus c. I want you guys to get from the place of just guessing. We're not about that life. The other Cal 2 kids are about that life, right? You make a step, there's a calculated decision for that step. And you make it based on certain best practices, right? You go through that process in your head that I told you about. Once you get your integral broken up into simple unit components, this is where all those formulas I had you memorize is going to come into play. Every step you make is simplifying towards some formula that you know how to take advantage of. So I don't want you to go in a test and be like, geez, this is similar to a problem that didn't class. What did Jhevon do again? Like, I don't want you to be that way. I want you to know why I'm taking every step I take. And I kind of told you why. But until you internalize both the strategies and the formulas, it's going to be very hard for you to see. And then it's going to be like you're just lost at sea out in the dark. You don't know what to do. You're just like out in the ocean, like on a piece of driftwood. Is land anywhere? Anyone see land? Like, I'm telling you how to find the lighthouse. The formulas are the lighthouse, right? Like you need to get to there. Oh, I know exactly what direction we should be going in now, right? The strategies tell you how to build your lifeboat. So now you're in a secure location. Now how do we get home? The formulas take you home. It's 50. Okay. Ideas?
Use of sign back.
Right, so this is going to be du over u times u minus 1. How do you figure that out? Cover method. You do that, do that. What goes on top of this guy? Integral?
Oh, negative ln of u plus, ln the absolute value would be plus.
Trying to die, kid? You trying to die, son? Okay. And now you just plug that in. So it's minus ln of sine of x plus ln of sine of x minus 1. Yes. Okay, so we already did this guy using trig substitution. Give me another way. Ideas? Yeah?
Can you do trig substitution?
Yes, we already did this using trig substitution. I want another way.
Oh.
This was one of our trig substitution examples. I want you to see another way of doing this. Yeah?
U squared equals, u sub u squared equals 1 plus x squared. So 2u dx equals 2x dx. Cancel out. And then, okay, so you get u over u squared minus 1. Well, and times u du, so it becomes u squared over u squared minus 1.
Explain that step a little more. Because
So,
we don't have x dx. How do you get that?
so like, you can bring the x over, like, so divide by x, and then you can plug in u du over x for dx, and that u multiplies with the u in the numerator, so that becomes u squared over, and you have the x in the denominator, so that becomes an x squared.
Yeah, that works. You could also like multiply and divide by x. That would be the same.
Yeah.
The x dx here is now your u du. And then the x times the x here gives you an x squared. You can solve for x squared from here. Your x squared is actually going to be u squared minus 1. This guy becomes u squared over u squared minus 1. And that guy we know how to deal with now. What is that going to become? You subtract 1, add 1, it's going to become 1 plus 1 over u squared minus 1. How do you do this part?
You factor it in cover.
Factor, do the cover up method. Right, so this part here is really just 1 over u minus 1 times u plus 1. So if I cover the u minus 1, plug in 1, I would get a half. Cover up the u plus 1, plug in minus 1, I get minus a half. So this all becomes u plus 1/2 ln of u minus 1 minus 1/2 ln u plus 1 plus e. Equals. U is now the square root of 1 plus x squared. plus 1/2 ln of the square root of 1 plus x squared minus 1 divided by the square root of 1 plus x squared plus 1. Sorry. F. Okay, ideas.
You could
Yeah.
do U substitution.
What would you substitute?
So U would be the denominator.
Your d is going to be?
D is going to be 3x squared plus 3 dx. And then you can factor out a 3 from U.
So your integral becomes?
So it'd be 1/3 integral of d du over U. That's
Which
just
is?
ln U.
ln of?
ln of absolute value.
Right. No partial fraction is necessary because that's straight up substitution. Now, had you forgotten the strategy and went on a journey to try to factor that guy, you'd have wasted like 20 minutes and then realized that it doesn't factor. If ever you'd realize that. That's actually. That being said, you won't need partial fractions for this one either, but for this one you would need to know how to factor the denominator to do it the easiest way possible. So I'm not going to go over that right now. Try this for next time and give you a hint, because I actually want you to look this stuff up. Rational roots theorem would be the hint. Using the rational roots theorem, you'll be able to figure out the answer to that. Now, what I want to do for the remainder of class is teach you one final technique. It's going to be pretty cool. I'm going to introduce it. We'll do some examples for, I'll give you some examples for next time, but for now let me just introduce this method. So, this is a new integration technique. It was developed by a mathematician by the name of Carl Weierstrass. He was a mathematician in the 1800s. And it is called a Weierstrass substitution. So this is a substitution named after a German mathematician, and basically what it is, you can kind of think of it as an inverse trig substitution. So remember what a trig substitution is about. You have something that has rational expression in it, like a squared minus x squared, a squared plus x squared, or x squared minus a squared, and you substitute a trig function in to actually transform it into a trig integral that you can hopefully do. The Weierstrass substitution method literally is the opposite. You're given a trig integral in the first place, you plug in an inverse trig function to transform it into a rational function, at which point you can do like a partial fractions or something like that. So it's kind of like the reverse of a trig sub. It's like when you have trig, you transform it to something with no trig in order to do it. Whereas trig sub is like you won't have any trig, but you transform it to something with trig in order to do it. So this is like an inverse trig substitution. So this is most useful for if you have integrand that is a rational trig function. So remember what a rational function is. It's like you have a ratio of polynomials, you know, like an x squared plus 1 over x squared plus 2x minus 3 or whatever, right? Just imagine that kind of function, but instead of x's, you have trig functions. So you'd have something like sine squared x plus 1 over sine squared x plus 2 cosine x minus 3, right? So if you see something like this, there's a technique that you do for that, but if you see something like this, then a Weierstrass substitution method might be something that you can try. So it's like you have a rational trig function. So it's rational trig function. It can work in non-rational cases, but those are a little bit trickier. I'll only ask you about the rational cases, right? So if you have a rational trig function, here's the substitution. You set u equals tangent of x over 2. Right? So that's the substitution. Now let's see what are the consequences of such a substitution. Well, notice what this would mean for trig function in angle x. Right, so x is like the angle. Now what would that mean for your actual x? Well, this would mean that your x would be what? How can I solve for x here? That'll be 2 tangent inverse of u, right? Now I can differentiate both sides. Derivative of 2 tan inverse of u. Derivative of tan inverse of u. 1 divided by 1 plus u squared. So this is 2 divided by 1 plus u squared du. So that's the first important equation. I can replace my dx with that expression. Now I want to know, how would I deal with the different trig functions in this scenario? Well, what we're going to do is figure out what would the sine x and cosine x be under this substitution. And then using sine x and cosine x, I can figure out everybody else. So if my u is equal to tan of x over 2, this means there's a triangle where the angle is x over 2. And my tangent is going to be opposite over adjacent, which means this is going to be the square root of 1 plus u squared. And so now how would this means, for example, that the sine of x over 2 would be opposite over hypotenuse, and my cosine of x over 2 would be adjacent over hypotenuse. So if someone were to ask you, what is sine of x under this substitution? Well, you can use the double angle formula. This is going to be 2 sine x over 2 times cosine x over 2. So that ultimately is going to give you 2 times this times that. You get 2u over 1 plus u squared. So it means you can replace any instances of sine x with 2u over 1 plus u squared. And that's another important equation. Similarly, if someone were to ask you, what is the cosine of x under this substitution? Well, I know that my cosine of x, using the double angle formula, that's cosine squared x over 2 minus sine squared x over 2. So it's going to be this squared minus that squared, or in other words, 1 minus u squared over 1 plus u squared. So that gives you another important equation. The cosine of x under this substitution would be 1 minus u squared over 1 plus u squared. Now, once I know sine and cosine, I can figure out what's tangent, what's cotangent, what's secant. I can figure them all out at will. But this substitution means you can replace dx with that, you can replace sine x with this, you can replace cosine x with that. So now notice that I have rational functions that are representing trig functions. Let's see an example of actually applying this. Suppose you wanted to do, where are my examples? The integral of 1 over 1 plus sine of x. Now, there's another way to do this, which we'll talk about afterwards probably, but let's actually use a Weierstrass substitution to attack this integral. Notice it is a rational trig function. So what I can do is I can apply my Weierstrass. What would that mean? Well, under the Weierstrass substitution, my sine of x can be replaced by this expression. And my dx can be replaced with the other expression that I had erased over here. Now, simplifying that, what is that going to look like? Well, that'll be the integral of 2 divided by, take the 1 plus u squared, multiply out the denominator, I would get 1 plus u squared plus 2u. So it turns that guy into this. Well, that's actually going to be u plus 1 all squared once you simplify it at the end of the day. How do you do that integral? You could do partial fractions. There's an easier way. Substitution, which you used to think of before partial fractions. Do t equals a u plus 1. Your du would equal dt. That's just 2 over t squared, which is 2t to the minus 2. So the integral of this is just going to be minus 2 u plus 1 to the minus 1 plus c. And what is my u? Well, it's tangent of x over 2. So this is minus 2 divided by tangent of x over 2 plus 1. That is the integral. Don't worry, it'll take a while for it to sink in. Don't panic. Some of you aren't following, it's fine. Before we move on, can you think of another way to do this? Say you didn't know about the Weierstrass substitution. What would you have done in that case? It's not so bad to actually do without it. Yes, about here.
Yeah, so no matter what, u is always gonna be equal to tan
X over 2.
x over 2.
Yeah.
Okay.
That specific substitution is the Weierstrass substitution. Yeah. U equals tan of x over 2.
And then from that, whenever you see a sign, you can replace it with
With the expression I get, whenever you see a cosine, you can replace it with that. If you want to replace a tangent, replace it with the division of those. And yeah, you can change any other trig function into a bunch of rational.
okay.
Now you'll get to a situation where maybe you need partial fractions, maybe you need something else, but they it should be easier than the original. That's the idea. That being said, another way to do this, ideas?
I
Yeah.
was thinking maybe to multiply with a reciprocal.
Which is?
1 minus sin x. And the top one.
Why did you want to do that?
So then you'll have,
Huh?
then you'll have cosine squared x on the bottom. And you'll have 1 minus sin.
Right, so because you know 1 minus sine squared is cosine squared, you had a formula in your head. That's what tells you you could do that. And in the top now you have 1 minus sine x.
Separate them.
You can separate those. That will be secant squared x
And then
minus, I mean, you're looking at sine x over cosine squared, I guess.
And then for the first one, that's the tangent x.
Yeah, that's going to be a tangent. What about this
That
one?
one, can't you do yourself, making the, maybe, I think it's just a
Right, you can do u equals,
3 equals cosine x.
your du is going to be minus sine x dx. So this is going to be equal to tangent x, which is the integral of the secant squared, plus the integral of du over u squared. So you have tangent x minus 1 over u cosine. Let's see. So you could also do that. Now, one thing I want you to consider for next time, are these both the right answer? Actually, both correct. But I do want you to think about why that would be the case. Why is this not a contradiction? How do we know that they're both correct answers? And what's kind of the explanation connecting these two answers? Other than that, for next time, try out these examples. So in addition to the example I asked you to do for the rational roots theorem, by Tuesday, also try doing these examples. Now you'll notice with this one, a trick like what you did here isn't going to work out. It's a 3 and a 2, that's going to be an issue. Trick like that also isn't going to work here. Now, way back when we were doing the integral of secant x, we kind of multiplied out of nowhere by this crazy expression, like why would anyone have seen that in the first place? Weierstrass provides a more direct method for finding the integral of secant x. Actually use the Weierstrass to do that. So essentially it's a technique where what you're doing isn't coming out of nowhere, but at the same time, in the beginning your answer is going to look sort of different from the answer that you know this to be. So I'd like you to show your answer is equivalent to the formula. You have memorized. So this is actually the last integration technique that I want to cover. Not that we're completely done with integration. We're going to do integration in other contexts, but in terms of fundamental integration techniques, things that you use to compute integrals, you now know 7 of them, right? You have basic rules, you have substitution, trig substitution, partial fractions, integration by parts, Weierstrass substitution. And those will be with you for the rest of your integration lives. Try those examples out and let me know what you come up with on Tuesday. So quiz on Tuesdays up to, of course, everything that we did here.
See you guys.